Somewhere out there, a single dying star has left behind an object no wider than a city, yet heavier than the sun many times over. Somewhere else, a shadow so enormous sits at the center of a galaxy that 100 billion stars are bound to it, wheeling around it for eternity. And between those two extremes lie things stranger still, objects that live only inside equations written into the mathematics of the universe, but never once caught in a telescope. Today, we're going to climb the entire ladder of black holes, one rung at a time, from the quiet corpses of collapsed stars to the most unsettling ideas physics has ever produced. But before we climb, we should be clear about what we're looking at. Peel away the legend, and a black hole is nothing more than a region of space where gravity has won so completely that escape becomes impossible. Not for a rocket, not for a radio signal, not even for a ray of light. Take the sun and picture crushing all of it into a ball only a few kilometers across. The gravity at the surface of that ball would grow so fierce that it would fold space and time inward on themselves, carving out a one-way door with no handle on the far side. That door has a name. We call it the event horizon, the invisible edge beyond which nothing returns. Cross it and you are gone. Matter, light, even information itself becomes part of the darkness, sealed away from the rest of creation forever. And yet, for all the dread they inspire, black holes are not monsters prowling the galaxy in search of prey. They don't chase down planets or hunt sleeping stars. They are simply what happens when the laws of physics are pushed all the way to their breaking point. Squeeze a giant star past the limit its own core can bear, or pile matter high enough in one place, or let the young universe fold under rules we barely understand, and a black hole becomes the only possible outcome. Here, though, is the part most people never hear. Not all black holes are cut from the same cloth. Some are born from stars only a handful of times heavier than the sun. Others swell into giants millions or billions of times that size, and a few exist only as predictions, sketched out by theory and still waiting for proof. That is the road ahead of us. Over the next chapters, we'll rise through 5 distinct levels of black holes and then push beyond them into stranger territory still. So settle in. The descent into darkness starts now. Every black hole story begins with light. Stars are the great furnaces of the cosmos, forging elements and holding back their own crushing weight with the heat of nuclear fire. But no furnace burns forever. When the heaviest stars run dry, they don't slip away in silence. They detonate in blasts so violent that for a few days, a single dying star can outshine every other star in its galaxy combined. And out of that wreckage, something remarkable can be left behind. Not every star earns this ending. Our own sun is far too gentle for it. When its fuel runs out, it will swell, shed its outer layers, and settle into a slowly cooling ember called a white dwarf. To make a stellar black hole, you need a heavyweight, a star at least 20 times the mass of the sun. When a giant like that exhausts its fuel, the core can no longer hold itself up. Gravity crushes everything inward, packing matter to a density that language struggles to describe. What survives is an object somewhere between 3 and 100 times the mass of the sun, folded into a sphere you could tuck inside a small town. Sit with that for a moment. A black hole only a few kilometers wide, carrying the weight of dozens of suns. If you swapped out the core of the Earth for one of these, our entire world would vanish into it in an instant. To match that density, you would have to fold an entire mountain range down into a single marble. So how do you find something that, by its very nature, gives off no light at all? The trick is to watch its neighbors. A black hole may be invisible, but the chaos it causes is not. When one orbits close to a living star, it can tear gas away from its partner. That stolen gas doesn't drop straight in. It spirals, coiling into a searing disk that heats to millions of degrees and blazes in X-rays, bright enough to cross the galaxy. Point an X-ray telescope at the right patch of sky, and those hidden traps light up like beacons. The most famous of them is Cygnus X1, spotted in the 1960s and sitting roughly 7,000 light-years away. It holds a black hole around 21 times the mass of the Sun, locked in a deadly waltz with a massive blue companion. The X-ray glow was so loud it could not be ignored, and over the decades the case became airtight. Even Stephen Hawking once bet against it being a black hole, and later admitted he had lost. Astronomers now suspect our galaxy hides millions of these dark remnants, most of them drifting silent and unseen. Cosmic ghosts we notice only by the clues they leave behind. If stellar black holes are the seeds of the family, and the giants at the hearts of galaxies are the towering trees, then something obvious seems to be missing. Where are the black holes in between? Objects heavier than a collapsed star, but nowhere near the scale of a galactic monster. Astronomers call these the intermediate black holes, and they may be the single most frustrating puzzle in this entire story. On paper, they almost have to exist. A stellar black hole tops out at around 100 solar masses. The giants weigh in at millions or billions. Common sense says the ladder should have rungs in the middle. Black holes weighing hundreds, thousands, maybe 100,000 suns. And yet, after decades of searching, they remain maddeningly difficult to catch. What makes them so important isn't just their size. It's what they might explain. They could be the missing link in the whole life story of black holes. The bridge that shows how tiny stellar remnants ever grew into the behemoths anchoring galaxies. Without a middle stage, it becomes very hard to explain how the universe built its largest gravitational giants at all. The trouble is that hunting them feels like chasing smoke. The largest black holes announce themselves loudly, blazing across the sky as they devour matter. Intermediate black holes stay quiet. They don't feed hungrily, they don't glow, and they rarely sit anywhere convenient. So scientists have to look for whispers instead of shouts. One of the best places to listen is inside a dense star cluster, a tight ball where hundreds of thousands of stars are crammed together. If something unusually heavy lurks at the core, it tugs on the stars around it, bending their orbits in telltale ways. In the cluster known as 47 Tucani, the motion of the stars hints at a hidden mass of roughly 2,000 suns, exactly the kind of object we've been looking for. Another clue comes from small, faint dwarf galaxies orbiting larger ones. A few of them appear to host black holes that fit neither category cleanly. One striking example lives in a source called HLX1, some 290 million light-years away, where the evidence points to a black hole around 20,000 times the mass of the Sun. It may be one of the cleanest intermediate candidates ever found. And still, the questions pile up. Why are these middleweights so rare, or at least so hard to see? Are they simply too quiet, hiding in corners where they never feed? Or does nature itself dislike making them, leaping straight from small to enormous by some process we haven't yet uncovered? For now, they remain the quiet giants we're certain must be out there, glimpsed only at the edge of our instruments. Now we come to the true titans. If stellar black holes are the seeds, these are the ancient trees whose roots run through entire galaxies. Supermassive black holes reach masses of millions, even billions of suns. And unlike their smaller cousins, they don't wander through empty space. They sit enthroned at the very center of galaxies, shaping everything around them. Look no further than home. At the heart of the Milky Way, about 26,000 light-years from Earth, crouches a giant known as Sagittarius A star. It holds roughly 4 million times the mass of the Sun, all packed into a region smaller than the orbit of Mercury. We cannot see it directly, but we can watch the stars nearest to it. They tear around that invisible point at staggering speeds, some completing a full loop in only a handful of years. Nothing but the gravity of a supermassive black hole could whip them along so fast. And our giant is modest by comparison. In the galaxy, M87, some 50 million light-years away, sits a black hole more than 6 billion times the mass of the Sun. In 2019, it became the first black hole ever photographed when the Event Horizon Telescope captured that now famous image, a ring of glowing gas wrapped around a perfect circle of darkness. It was humanity's first true look at the rim of an abyss. To picture the scale, remember that stellar black holes are city-sized. A supermassive black hole can be larger than our entire solar system. But the great mystery is where they came from. Collapsing stars can't explain them. No single star is heavy enough to leave behind something millions of times the mass of the Sun. One idea is that they started small and grew over billions of years, swallowing gas and merging with one another again and again. Another is that in the young universe, colossal clouds of gas skipped the star stage entirely and collapsed straight into black holes. We honestly don't know yet, and solving that riddle may reveal how galaxies themselves were built, because these giants are not passive. As matter spirals in, it can release ferocious floods of energy, powering quasars, beacons so brilliant they can outshine every star in their galaxy at once. The winds they drive can blow gas clear out of a galaxy, throttling the birth of new stars and steering the galaxy's entire evolution. In this way, supermassive black holes are destroyers and architects at once, both smothering starlight and setting the rhythm of galactic life. Nearly every large galaxy we've studied seems to guard one at its core. Without them, the cosmos we know might never have taken shape at all. Every black hole we've met so far was born from stars or grew inside galaxies. But what if some black holes are older than any star? Older, in fact, than galaxies themselves? What if a few of them formed in the very first breath of the universe, in the fraction of a second after the Big Bang? This is the idea of primordial black holes, hypothetical fossils left over from the dawn of time. They would owe nothing to collapsing stars. Instead, they would have formed when the universe was younger than a single second, back when everything was a boiling, ultra-dense soup. In that furious early moment, tiny ripples in the fabric of space could have piled matter so densely in certain spots that it caved in on itself and sealed off into a black hole then and there. If they exist, they could come in a wild range of sizes. Some might be no larger than an atom, weighing only a few grams. Others could rival mountains or asteroids in mass. Imagine a black hole smaller than a grain of sand, yet heavier than Mount Everest. That is the strange arithmetic we're dealing with. Why should anyone care about objects we've never seen? Because they might solve one of the deepest mysteries in all of science: dark matter. For decades, astronomers have noticed that galaxies spin far too fast for the amount of visible matter inside them. Something unseen must be holding them together, and no one knows what it is. One tantalizing possibility is that this hidden mass isn't made of exotic particles at all, but of countless primordial black holes drifting quietly through space. If that's true, then most of the matter in the universe would literally be invisible black holes, scattered everywhere around us. There's more. If primordial black holes seeded the early cosmos, they might also explain a stubborn problem: the fact that enormous supermassive black holes already existed less than 1 billion years after the Big Bang. Ordinary star-born black holes simply shouldn't have had enough time to grow that large. But if primordial black holes gave them a head start, the timeline suddenly makes sense. So far, the evidence is thin. We've never confirmed a single one. Scientists search for them indirectly, watching for the faint way their gravity might bend the light of a distant star, or for bursts of radiation that could flare up if a tiny one evaporates. Each new telescope offers another chance to catch one in the act. For now, they remain ghosts of theory, but ghosts that could rewrite the story of how everything began. We tend to imagine black holes as enormous things, the crushed hearts of stars, the anchors of galaxies, but what if a black hole could exist at the opposite extreme, smaller than a single atom? This is the strange and deeply theoretical realm of quantum black holes. These would belong to a frontier all their own. They exist in the narrow zone where our two greatest theories collide. On one side stands Einstein's relativity, which describes how gravity shapes the universe on the grandest scales. On the other stands quantum mechanics, which rules the flickering, unpredictable world of the smallest particles. Normally, these two theories keep to their own territory and never meet. But squeeze matter down to almost unimaginably tiny sizes, and both sets of laws demand a say at once, and neither one is fully equipped to answer. This is where the idea of Planck-scale black holes appears. The Planck length, around 10 to the minus 35th of a meter, is thought to be the smallest meaningful measure of space that exists. A black hole at that scale would be inconceivably small, far tinier than a proton, yet still hold an outrageous density. In theory, it would be the exact point where gravity and quantum physics finally have to share the same table. But there's a catch, and it's a big one. Small black holes don't last. Thanks to Stephen Hawking's famous insight, we now believe black holes slowly leak energy away through a process called Hawking radiation. For a stellar or supermassive black hole, that leak is so gradual it would take far longer than the current age of the universe to matter. But a black hole the size of a particle would evaporate almost instantly, flashing its energy back into space and vanishing before you could blink. Could such things ever have existed? Some scientists suspect they might have formed in the violent conditions of the newborn universe, when energy was crammed into space at unthinkable levels. Others wonder whether the ferocious collisions inside particle accelerators, like the Large Hadron Collider, could briefly conjure one into being. So far, no experiment has found a trace of them. Even so, the idea is far from idle. Quantum black holes force physicists to confront the single hardest problem in the field: how to weave gravity and quantum mechanics into one unified theory. If we could show that even a fleeting quantum black hole is real, it would be a priceless clue toward a theory of everything. These objects aren't about swallowing stars or sculpting galaxies. They mark the exact place where our current understanding runs out, and where entirely new physics would have to begin. We've climbed all 5 levels, from the corpses of dying giants to the ghosts of quantum theory. But the story doesn't stop at the top of the ladder. Beyond these categories lie other black holes, some already discovered, others still pure imagination. Think of this as the bonus round, the place where hard science and daring speculation stand side by side. One of the most thrilling discoveries of recent years is the binary black hole. 2 of these objects trapped in orbit around each other. For eons they circle, spiraling ever closer, until at last they slam together and merge in a single staggering release of energy. When that happens, the collision sends ripples racing outward through the fabric of space and time itself. We call those ripples gravitational waves, and they were detected for the very first time in 2015. That single detection confirmed both Einstein's century-old prediction and the existence of black holes colliding in distant galaxies. Every new signal since then adds another verse to a hidden cosmic song we only recently learned to hear. Then there's a far stranger notion: the white hole. If a black hole is a place where everything falls in and nothing escapes, a white hole would be its exact opposite. A region that nothing can enter, from which matter and light only ever pour out. None has ever been observed, and most physicists doubt they exist in nature. But the mathematics allows them, and a few bold theories even imagine a white hole as the far end of a black hole, the two joined together through a tunnel in space and time. It remains firmly in the land of what if, yet it captures the imagination like little else. These oddities remind us that black holes are more than astronomical objects. They are thought experiments made real, endlessly testing the limits of what we can measure and what we can dream. So we've reached the end of the climb. From the collapse of massive stars to the flicker of the quantum world, black holes have shown us a universe far stranger than the one we thought we lived in. We've seen them as small as an atom and as vast as billions of suns, bending time, anchoring galaxies, and quietly rewriting the rulebook of physics. Stellar, intermediate, supermassive, primordial, quantum, 5 levels, each one prying open a deeper mystery. What lingers most is the sense of escalation. Black holes are not merely engines of destruction, they are doorways into the question of creation itself, humbling reminders that the cosmos still guards secrets we've barely begun to read. The universe keeps its darkest objects hidden in plain sight, waiting for us to look closer, subscribe, and follow the light all the way to the edge of what we know.